This is September 2010. Question 1. MEN switchboards have got characteristics not found on distribution boards. So we want two characteristics. Now an MEN board will have a link between the neutral and earth busbar. You'll have a connection to earth via the earth lead to an earth electrode. It's closest electrically to the point of supply, and it can supply another MEN switchboard. I think the first two are the easiest to remember, the MEN link and the earth via the earthing lead to the electrode. B. Why do three-phase induction motors run smoother and quieter than single-phase induction motors? Well, it's all about that rotating magnetic field. They have a constant rotating magnetic field. C. Two reasons for using reduced voltage for starting three-phase motors. So reduced voltage will give us reduced starting current, it will give us reduced voltage surges, and it will limit the mechanical shock. D. Class 1 electrical appliance that incorporates a MIMS element. Now as soon as you see this MIMS, alarm bells should start ringing because they're a special thing when it comes to insulation resistance. So they're asking for the permitted insulation resistance test result. Now usually we talk about 1 mega ohms for insulation resistance, but if there's MIMS in there, it's 0.01 mega ohms or 10,000 kilo ohms. So we're allowed a lower insulation resistance. The earth conductor test is still the same though. We're still looking for 1 ohm maximum. So the MIMS doesn't change that, it just changes the insulation resistance. Two factors that limit the prospective short circuit current in a supply. So what's the maximum short circuit current we can get? Well, it's going to be dependent on the capacity of the supply source. So the power, the MVA of the supply, how much it can push out. The impedance of the transformer, because the current is going to be voltage over impedance over Z. The circuit impedance, so both of those impedances, and the length of the cable between the transformer and the main switchboard is going to limit the current. Why is the secondary terminal voltage of a transformer less at full load than at no load? I think we saw this one in another paper. There's an internal volt drop due to the impedance of the winding. So the current flowing through the windings causes a volt drop within the windings, and so the voltage you get on the outside of the transformer is going to be less. If the burden of a current transformer is increased, what practical effect does it have on the primary current? It's not going to change the actual primary current, so no effect. Typical secondary voltage of an instrument voltage transformer. So they give you two, 110 and 63.5. I generally just remember 110, so you get 110 volt instrument voltage transformers. Ohm meter gives a reading of 24 ohms measuring the resistance of a heater, and it can be used on 230 or 240. It draws 10 amps when it's connected into a 240 volt supply. So it's one of these, calculate the difference in the power from the 240 to the T230. So we need to calculate the power for both instances, which they've done here. So power is V squared over R, so a very important formula. Need to know that going into this exam. For the voltage being 240, we've got 240 squared there divided by 24 gives us 2,400 watts. If we decrease the voltage to 230, 230 squared over 24 gives us 2204, and what they're looking for is the difference, so we minus that from the 2400 and we get 195.83. I would knock them half a mark there because they haven't put the watts. So 195.83 watts. Explain why earthing the metal frame of a class 1 electrical appliance prevents electric shock under fault conditions, and why it ensures in relation to protective device. So under fault conditions, it will keep that frame at earth potential, at 0 volt potential. And in relation to the protective device, it will make sure it operates basically. It will give us a low resistance to give us lots of current to make that device operate. Minimum value of permitted test result for insulation resistance. So insulation resistance, 1 mega ohm, should trigger that straight away. 400 volt mains cable, so don't be fooled by the voltage, it's still 1 mega ohm. Here we are there. The maximum value of permitted test result for an earth leakage. So the earth leakage test, we can allow up to 5 milliamps to flow. So that's our maximum value, 5 milliamps. And this question 2 is quite a weird question, and the answers seem very basic, but go along with it. So we've got 3 fluorescent lights here, each protected by their own 1 amp fuse, 16 amp MCB and an RCD protected. So it says, how is discrimination achieved in the figure above? Well, discrimination is achieved because we've got a lower fuse at the fitting and a higher rating MCB protecting all of those fuses. So their answer, each fitting has a 1 amp fuse, the circuit is protected by 16 amp MCB. Which part of the circuit are protected by the MCB? So it protects the whole of the circuit. So that 16 MCB is protecting all 3 fittings. State 2 types of fault the MCB provides protection for. So it provides protection for short circuit, which would be the magnetic thing inside the MCB, and overload, which would be the thermal bimetallic strip. So the 2 things, short circuit, overload. Which parts of the circuit are protected by the HRC fuse in fitting A? Which parts of the circuit are protected by the HRC fuse in fitting A? And that answer is, it protects fitting A. State 2 types of fault the 1 amp HRC fuse in fitting A provides protection for. So again, that HRC fuse can provide short circuit and overload protection. See what I mean about it? Seems too easy about what that's doing in fitting A. It's protecting that fitting. That's what they want you to be able to understand. Which parts of the circuit are protected by the RCD? So it protects the whole of the circuit. What type of fault does the RCD provide protection for? So it provides an earth fault on the circuit. So it won't provide protection for short circuit or overload, only for earth leakage faults. Phase to neutral short circuit has occurred in the cable between the light switch and the first fluorescent light. Which protective device will operate to clear the fault? So if we've got one between the light switch and the first fluorescent, there's the light switch there and the first fluorescent is in there somewhere, then the MCB is going to protect it. Where are we up to? State 2 reasons why the 1 amp HRC fuse in fitting B must not be shorted out or increased in rating. So the MCB would operate disconnecting all the lights in the circuit. So if we had a dead short across that 1 amp fuse in fitting B and there was a fault in that fitting, the MCB would operate and then all the lights would go out. The wiring and components in fitting B may have a much lower current rating. So if we short out that 1 amp fuse and 2 or 3 amps flows through it, we could damage the fitting. The MCB may not trip and cause a shock hazard due to a faulty wiring. So if we lose that protection in the fitting by shorting out this 1 amp HRC, then we could cause a problem within the fitting, and that could cause an electric shock. Question 3, 3-phase 400 volt induction motor, and we've got star delta starter 230 volt control circuit. We've removed it for cleaning. We're going to check it's safe. Describe the test. Test the motor and attach cables to identify the windings before carrying out an insulation resistance test. So how we're going to identify the windings? We're going to use an ohm meter, and we're going to test between the cable ends, and we're going to look for a low resistance. And a low resistance is going to indicate the winding. And obviously each of those windings must have the same or very similar resistance. And that's how you know you've got the two ends of one winding. We're going to do an insulation resistance test. So type of instrument, insulation resistance tester, don't say mega. Minimum or maximum test values that are appropriate. So we're going to use a test voltage of 500 volts DC. Always put the DC in there. We're going to test between each of the three windings. So you're going to go between winding 1 and winding 2 and make sure that they're not connected. Make sure there's a good insulation resistance between them. And then 2, 3, 3, 1. So between each of the three windings. And then you're going to test between each of the three windings and the motor framework earth to make sure none of those windings are touching earth. Each test result must not be less than 1 mega ohm. So there's our 1 mega ohm for insulation resistance. 3 other checks or tests that should be carried out before reconnecting it. So we're looking at protective earthing conductor continuity test, a visual test, polarity test, and checking the integrity of the terminations. So I'd be remembering those 3 there really. Your earthing, visual, polarity. Question 4, we've got a 3-phase star connected kiln that's going to draw 25 amps from a 400 volt supply, and it's protected by a 30 amp fuse. Now we've got a fault of 7 ohms within the kiln, and we've got a protective earthing conductor resistance of 0.5. So that 0.5 is less than our 1, so everything should be okay with this situation. So calculate the total current in the red phase. Now the trick here is that the total current is going to be the normal current, the voltage divided by this fault plus this resistance here, and then the total current is going to be that fault current plus the normal current, so this 25 amps here. So to find the fault current, we do 230 volts, which is our voltage, our phase voltage, because it's a star connected pottery kiln. So 230 volts divided by 7 plus 0.5, which is that there, which gives us 30.66 amps. So that's the fault current. The total current in that red phase is going to be that fault current plus the 25 to give us 55.66. Now we're going to determine whether the 30 amp HRC fuse is going to blow, is going to operate. Now the fuse has got a fusing factor, we're told, of 1.5. So that means it won't blow at 30 amps, it won't blow at 35 amps, it will blow at 1.5 times 30 amps. And 1.5 times 30 over here is 45 amps. So we need 45 amps for that fuse to blow. We've got a total current of 55.66, so the fuse will operate. So you need to show the calculation of the fusing current. You need to state what the total current is, and you need to say that it will operate to get your maximum marks. Now it's the same kiln, same fault here, but we've got an earthing conductor now of 12 ohms. So that should ring alarm bells in your head. 12 is way too high. The total current, that fault current, is going to be much lower. So let's have a look at that. We've got 230 divided by 7, which is our fault, plus 12, which is our conductor resistance. And that only gives a current of 12.1. And if we add that to the 25 of the normal red supply current, we get 37.1. So again, will the fuse operate? Well, we've only got 37.1. It's much less than 45, and so I would say it would not operate. They would also accept the fuse may take a long time to operate, because that kind of current may eventually blow that fuse, but it's not going to be instantaneous. Determine, using calculations, the electric shock hazard voltage the protective earthing conductor resistance at 12 ohm presents to the user of the kiln. So current flowing through 12 ohms is going to cause a volt drop, so we could get a shock from that volt drop. So the volt drop is going to be I times R, V equals I times R. We've got 12.1, which is our fault current from back here. So 12.1 times 12 gives us 145.2 volts. So there's a shock hazard of 145.2. Question 5. We've got a 230 volt, 2 kilowatt class 1 single phase heater plugged into a socket outlet. There's our socket outlet there. So there's our heater. There's our three phase supply, and we're coming off, it looks like there, we're coming off of the white line there. So we're taking the white phase to the socket outlet. Would normally just go through the appliance like that, but we've got a fault going down here, back through the MEN link, back to the neutral. So it's on the diagram below, draw in the earth fault loop. So the earth fault loop would be through that white line, down to the socket, through the fault, through the casing, the earthed casing, through the earth conductor there, back to the MEN link, through the MEN link, back up to the neutral and to the neutral of the transformer, which is shown over here with these arrows. The fault has an impedance of 60 ohms, between which 2 points is the 60 ohms impedance. So the 60 ohms is that fault there, so it's between A and B. The protective earth and conductor has resistance of 0.5, so where's that? So that's there, that's between C and D. And the fault loop impedance of the circuit supplying the socket outlet is 0.67. This was measured before the appliance was plugged in. So it's before this was plugged in here. Between which 2 points would the impedance have been measured? So they would have had to measure it between D and E. So that would have been measuring the fault loop impedance back there. So between D and E. Calculate the total current in the phase conductor under the fault conditions. Now this is another one where you need to find the fault current, and then you need to add the normal current. So let's have a look how they've done it here. The normal current, the current in the load, would be the power divided by the voltage. So you're given the power here, it's a 2 kilowatt heater. So 2 kilowatts, 2000 watts, divided by 230 gives me 8.7 amps. That's the normal current flowing in the circuit. But we've also got a fault, and that fault is made up of the 0.5, which is the protective earth and conductor, the 0.67, which was the earth fault loop impedance, and the 60 ohms, which is the impedance of the fault. So that's quite a high resistance there. Gives me 3.76 amps. If we add those two together, you get just over 12 amps. Question 6. You've installed a single phase socket outlet and circuit wiring. 4 tests using test instruments other than insulation resistance. So there's our 4 there: polarity, earth continuity, earth loop impedance, RCD tests. Of the tests, which must be carried out with the circuit live? So we're only looking for one. So we can have earth loop impedance test, RCD, or polarity. So they can be carried out live. And then what they're asking you to do here is, for the one that you've said there, answer this question about type of meter, maximum minimum values that apply. So they've gone through each of the ones there: earth loop impedance, RCD, polarity. I would be answering the RCD one if this was me. Much easier. Use the RCD tester, plug it in, make sure it operates within that 300 milliseconds with a maximum of 30 milliamps. But you can describe any of those tests. C is looking for tests that you've got to carry out once it's been disconnected. So these are going to be your earth continuity are your polarity. And again, you're asked to describe one of those here. I think I'll be looking at earth continuity, using an ohm meter, testing between the earth, the plug and the switchboard earth bar, and looking for a reading low enough to operate the protective device. So it's not 1 ohm or half an ohm or anything like that. It's just a reading low enough to operate the protective device. Question 7, we're looking at a DOL starter. Now, I must admit I've never seen the DOL drawn like that, because they're asking for it to be drawn without the main contacts or the motor. So you're just looking at the control circuit. So the phase to a start switch, stop switch, overload, coil and fuse in both parts there, and we've got a hold-in contact that's operated from that coil in parallel with the start. So when we press the start, coil energizes, motor comes on, it operates this contact as well, and so when we take our finger off this button, we still get the supply through the holding contact, and we can stop the motor by pressing this stop button, which de-energizes the coil, de-energizes the holding contact. Redraw the start and stop buttons they've drawn, so we can use a remote start stop. So there's our remote start stop, there's our normal start and stop, and if you look, the remote start is in parallel with the normal start, and the remote stop is in series with this stop here. So we break between the start and the stop of the original contacts, and we take those leads out to the stop. So start in parallel, stop in series. This electrician has put this remote in, and after we've looked at the motor, turned the motor on, we can start it, but we can't stop it. So what that suggests is that these stop buttons have been put in parallel rather than series. You can see that the stop buttons have been wired in parallel, and so just breaking the stop buttons won't break the supply to the motor. Question 8, we're looking at an RCD. So in the previous paper there was a 3-phase RCD. This is just a single phase RCD, so nice and easy. Got your toroid, your phase and neutral, your live and neutral going in to your load. Test button between the live and the neutral with a resistor in there to limit the current. So we just want a little trickle of current flowing down there, and off of the main toroid, a sensing coil going up to the tripping device connected mechanically to the 2 contacts there, and an earth off of our class 1 equipment. So know the RCD when you go into this theory exam. The RCD test has been carried out on a portable RCD device. It's passed. What additional checks? Well, we want to make sure that when it goes off, that it doesn't come back on when we restore the supply, so that it's voltage dependent. It won't automatically reset if we restore the supply. Phase and neutral have been transposed. Is that going to affect the RCD operation? It's not going to affect it. So would it still operate? Yes, because it's looking for an imbalance regardless of the polarity of the supply. It doesn't care if phase goes in first or neutral. It's just if they're both the same currents, then it won't trip. A couple of different RCDs. PRCD, portable residual current device. RCBO, residual circuit breaker with overcurrent protection. And SRCD is a socket residual current device. Question 9, we've got a 3-phase voltage to a factory, and we want an uncommon voltage, so it's good old transformer calculation. 150 kVA, delta to star, and they've given you the turns ratio 43.3 to 1, and we've got 11 kV on the primary. So draw the circuit of diagram. So they've drawn the circuit diagram like that. There's our delta, there's our star, and we've got the star point earthed. I would tend to put some windings in there, but if they're okay with that, then you can do that. Calculate the secondary phase voltage. So the primary phase voltage is 11 kV. We've got 11 kV across there. Because it's delta, the primary phase and line voltage is going to be exactly the same. So it's going to be 11 kV on that phase. And so on this phase here is going to be 43.31 less than over here. So we've got 11 kV divided by 43.3, which is our turns ratio, gives me 254 volts. Now that 254 volts is the phase voltage. We're asked then to find the secondary line voltage. So the line voltage of a star is √3 bigger than the phase voltage. So our 254 times √3 gives me 440 volts. And that 440 volts is across the line voltage there. Calculate the primary line current. So the primary line current is going to be the kVA divided by √3 times the voltage. Because this is our power. Power is IL VL √3. So when we transpose, I is equal to the power divided by √3 times VL. Now they've done kVA times 1000. The kVA is the 150. So it's 150,000, which is down here. 150,000 divided by √3 times 11,000. The only problem with this calculation, you need to either put this in brackets on the bottom there, or do that, find the answer to that, and then do 150,000 divided by that. Don't do straightforward 150,000 divided by √3 times 11,000, because you won't get this correct answer. So if you do it correctly, put some brackets there, we get 7.87 amps is our primary line current. The secondary line current is going to be a similar calculation. The power of the primary and the secondary, or the kVA, is exactly the same, 150 kVA. So 150,000 divided by √3. The only difference now is our 440 volts that we've calculated up here, our line voltage 440, and that gives us 196.83 amps. So a much higher current in the secondary. As a primary and secondary. B, one practical method to reduce iron losses when a transformer is being constructed. So the classic answer for iron losses is that the core is laminated. So it's made up of laminations. It's not a solid core. And that stops out eddy currents and iron losses. And we can also use special types of alloys to make the core that will reduce the eddy currents, will reduce the iron losses.